Alright, what up, ladies and gents? This is the first section in Calculus BC. BC is very similar to AB. There's only like 2 or 3 new units. Most of it's very, very similar. We're going to start off with limits, go into derivatives, go into integration, very similar to what we did in, BC, in AB. And then we're going to add some sequences and series at the end, along with some Taylor series and Maclaurin series and all that other garbage at the end. But for right now, let's get started in this. Okay, you will be using a textbook in this class. I will have it on PowerSchool, and it will be just a digital copy. It will not be a hard copy. And these are the pages you'll have homework, or these are your practice questions. These will be the questions that you'll have to do, pages 55 to 58 and so on and so forth right there. The answers will be also on PowerSchool as well, with all the work shown, so you can definitely see if you're right or wrong. You should be able to fly through these first couple of units because it's very similar to what you did last year. So let's get started. These videos shouldn't be too long. I'm going to try to get through these as fast as possible, just so that you can I guess finish with what you need to finish and then get into series and sequences and things like that. So calculus section 1.2, we're talking about limits. We're going to estimate a limit using a numerical or graphical approach. We're going to learn different ways that a limit can fail to exist, and then learn how to write a limit. So again, this should be review. That's why this stuff should be able to fly through. The limit is the value of f of x as x approaches a certain number. The limit is just written, okay, this is our notation, right, lim, as x approaches some value c of the function is equal to L. L is that limit, where lim is the abbreviation, and so on. You can read all that. I'm not going to go through a lot of this stuff. That's very similar. Okay, so the limit is read as the limit as x approaches c of f of x equals L, or the limit of f of x as x approaches c of f of x equals L. That's how we would verbalize this notation right here. But other than that, that's pretty much where we need to stop or end there. So let's get into some examples, because this is kind of really what we care about. Limits aren't that big of a deal on the BC test. I mean, you still need to know them, but it's not going to be as much like on the AB test, and that's not even that many on the AB test. So first thing I want to do is I want to find the limit of a function numerically. So here's a function of a limit, or here's a limit as x approaches 1 of the function. So let's kind of do it numerically. So I'm going to pick values to the left of 1 and pick values to the right of 1. And I made a box here, and you can see what's going on. So I'm picking numbers from the left of 1 and picking numbers from the right of 1. I need to find out where it approaches both sides. If it approaches the same value on both sides, then that's our limit. So if I plug in 0.75 to x into these, I can definitely do that. So if I do that, I get 2.3125. Let me pull up my calculator and kind of show you a way to do that, maybe easily. I'm not sure if it's going to be easy or not, but I don't know why we got to do this every single time, but there we go. Let's move it over here. Okay, so I can definitely store the function in here. So x to the third, where's x at? X to the third, oops, that's x squared. 'Tis not right. X to the third minus 1. Remember, I should have put parentheses in the beginning, shouldn't I have? Remember, make sure you do that, please. And then divided by x minus 1 in parentheses. Okay, x minus 1. So if I do that, and I go to my table, actually I'm not going to go to my table, I'm going to go to my table set. I'm going to turn this into independent into ask. This is the easier way to do it. And then go to my table, second table. I'm going to ask it what 0.75 is. Hit enter. I'm going to ask it what 0.9 is, and so on. You can do that to 2.71. I'm going to stop it there. I'm not going to do the rest. You can do the rest if you want to know. So I'm going to get out of my calculadora here and get going. So 0.99, I get 2.4701. I'm sorry, 9701, not 47. Sorry, my handwriting. And then 2.997. At 1, it does not exist. All right. At 1.001, I get 3.003. I get 3.0301. I get 3.31 and 3.8125. So what's going on here? We can see that the limit is growing to something, and then it's going up and up and up and up and up. But it's condensing to one number. So it's coming down here to one number, it's going up to one number, and it's actually probably going to arrive at 3. If I look at 2.997 to 3.003, that's going to arrive at 3. So the limit as x approaches 1 of f of x, and you can write the function there if you want to, that is equal to 3. Okay, we can definitely see that there. Now, what I can do is, there we go. I can find the limit of a function geographically. So it's the same function. This is just the graph of it. And I'm trying to go to 1 here. So 1 is going to be like up in here. And I can see that I'm going up and I'm coming down. Alright, so that is why it arrives at that. But realistically, if you think about it, at 1, there's probably going to be a hole there. So at 1, there's a hole. So if I go up and over, you can definitely see that it's going to arrive at 3 from both sides. So that's the graphic approach to it. So I get the same answer as the first example there of being 3. So same thing there. So now, next example, if I have this limit here, this function here, x over square root of x plus 1 and then minus 1, I'm going to draw this. So there should be right around there. I believe there's probably going to be a hole right here. And it's going to go on, just like that. And there's some other points, and you can put some points there as well. All right, so I'm going to say I want to, as it's approaching 0, so you're basically saying the limit as x approaches 0 of f of x equals some value. We got to find that value. So if I'm approaching 0, I'm going to put 0 in the middle. I'm going to say this is negative 0.001, negative 0.01, negative 0.1. This I'm going to say is 0.001, and then 0.01 and 0.1. And again, you can use your calculator to determine what those values are, but they are going to be 1.949, 1.995, 1.999. This does not exist right there. 2.004, might be another O there. I think there's 3 O's. This is 2.005, and then 2.049. All right. So we can see that it's approaching 2 from this side, it's approaching 2 from this side. So I'm going to guess, no, it's not really guessing, right? We're using mathematics, that the limit is going to be 2. Okay? Fantastic. So, even though, so f at 0 is undefined, right? Just because it's undefined, that doesn't mean anything. We can still find the limit because both sides are still approaching that 2. They're still coming to the same thing. If one's higher and one's lower, then yeah, of course we don't have a good limit, and same thing vice versa. But if we're approaching from both sides and it's the same value that it's approaching, regardless of it being the fact that it doesn't exist at that point, it still is okay to be that value. Okay, so f of x is still going to be 2. It's still approaching 2 at that value. Okay, in general, the limit exists for a function if the left and right limits approach the same thing. So that's what I just talked about. So if they're approaching the same thing, boom. If they're not approaching the same thing, that's wrong. This is regardless of the fact, dang, that's a good word that I just used, of whether the limit is equivalent or the limit exists at that point. So if it's an open hole, that's basically saying, again, if it's an open hole, as long as they're condensing to the same value, that's okay. Okay, so this here, just because this is what we call a piecewise function, just because the piecewise function is basically on 1 all the way through, but at 2, it equals 0. And it's still going that way. So this limit is still 2 because both sides are approaching that. I'm sorry, it's not at 2. It's at 1. The y value is at 1. So it's because it's still approaching the same thing from both sides. It's not different on both sides. It's the same. Okay? Great, 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 great. What else? Limits that do not exist. Limits that do not exist, the left and right. Oh, that's not right. R-I, oh my gosh, I can't spell. Let's see, R-I-G-H-T, there we go, are different. So the limit as x approaches 0 of the absolute value of x over x is equal, well, if it's approaching 0, this limit here is going to approach -1. That's the left side. So the limit as x approaches x approaches 0 from the left is equal to -1. But the limit as x approaches 0 from the right is equal to +1, because that's up here. So -1, +1. So this one is a does not exist. They need to be the same value from both sides. I mean, that's pretty self-explanatory, hopefully. Okay, we have a couple things called unbounded behavior. Alright, so we have this function, the limit of x approaches 0 of 1 over x squared. So this one here, because the value is going up on both sides, it's not approaching the same value, so it still is a does not exist. But you could also say that it's approaching positive infinity, because it really is going up and up and up and up. Like 0 is going to be like a vertical asymptote, right? And so it's approaching positive infinity from both sides. So theoretically, you can write both of those, and that would still be correct. But if we want to be more specific, because infinity is not an actual constant, it's not an actual value, so this is not a constant like an actual number, okay? This is probably not the best number to use, but it would still be okay. So does not exist is probably better to use here, but infinity would be okay in that regard. What else? Next one. 1 over x to the third as it approaches 0. This one here, I cannot say this one is infinity, or I cannot say it's negative infinity, because one side goes up and one side goes down. So this one is a more better answer, does not exist, because it's just better, because they're approaching different things, right? One's going up, one's going down. So this one is definitely better. It does not exist. The last two there, we have some oscillating behaviors. All right. This one is x as it approaches 0 of sine of 1 over x. This is a does not exist as well, because this is what we call oscillating. I can't spell. Hopefully I spelled it. Yeah, I did. What that means is the sine function, right? Remember, it goes up and down and up and down and up and down. And so it's oscillating between different values, between -1 and between +1 and -1. And here, it's oscillating between those two values, but at any given point, it's not condensing to one number. So it could be really high here, really low, really high, really high. So it just alternates, way too much alternating, oscillating behavior to determine if this is a real limit or not. So that's why this one is a does not exist. There is an exception, and that's right here. You can see it's really, really big time unbounded. So it's really big values. But then all of a sudden, as it's getting closer and closer to 0, all right, it's definitely getting smaller and smaller and smaller. And then on the other side of 0, it's smaller, smaller, and then it's getting bigger and bigger and bigger and bigger. So it's getting bigger, 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 smaller, 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 bigger, bigger, bigger. So you can see that it's condensing into one number. So this one does condense into 0. So yeah, that's it for this lesson. Hopefully it's not too long. Hopefully it's just a good repeater. Remember, do the homework up there. And in this class, you will not have power assignments after every lesson, especially for the first review units of AB. So you might only have one quiz in all of Unit 1, or might have 0. I don't remember exactly how I did it, but that'll be in Power School, and I'll give you a syllabus and all that stuff. But that's your homework. That's your practice problems right there. If you have any questions, let me know in class. But other than that, deuces.